Hi, Stu Schwartz from MasterMathMentor.com. This is video BC07c. The topic is center of mass and it covers the BC manual pages 173 through 176. Mass is a measure of a body's resistance to change in motion and is independent of gravity. However, because so many applications involving mass occur on the Earth's surface, we tend to equate an object's mass with its weight. This is not correct. Weight is a type of force and dependent on gravity. If there is no gravity, there is no weight. So a spaceship in outer space has no weight, but certainly has mass. Force and mass are related by the equation force is equal to mass times acceleration, or mass is equal to force divided by the acceleration. In the United States, force is measured in pounds and mass is measured in slugs, which are pounds per feet per second squared. Internationally, force is measured in newtons and mass is measured in kilograms, which are newtons over meters per second squared. In number 1, we are told that J is a student weighing 150 pounds at sea level. We'd like to know his mass and his weight on the moon, where gravity is 5.322 feet per second squared. In order to do this, we have to find J's mass, which is independent of gravity. This is 150 pounds divided by 32 feet per second squared, which is the force of gravity on the Earth. And we get 4.688 slugs. From there, we can calculate his weight by using the formula 4.688 is equal to W divided by 5.322. And therefore, his weight on the moon is 24.949 pounds. So an object will have about 1/6 its Earth weight on the moon. Suppose we have a mass m concentrated at a point. If x is the distance between m and another point P, we define the moment of m about P as moment is equal to mx. To illustrate, suppose we have two animals sitting on a seesaw. Chessie, the dog, weighs 6 kilograms and sits 6 meters to the left of the fulcrum P. Finucci, the cat, weighs 5 kilograms and sits also 6 meters to the right of the fulcrum P. The seesaw would rotate counterclockwise, moving Chessie down and Finucci up. This occurs because the moment produced by Chessie is greater than the moment produced by Finucci. Chessie's moment is 6 times 6, which is 36 kilograms meters, and Finucci's moment is 5 times 6, or 30 kilogram meters. To balance the seesaw, the two moments must be equal. Now, the animals are not going to change their mass, so one of them has to move. And Finucci cannot move any further right to increase the right moment. So Chessie must move right to decrease the left moment. And it should be obvious that if Chessie moves 1 meter to the right, then the left moment becomes 6 times 5, or 30 kilogram meters, and the seesaw will balance. Suppose several point masses are located on the x-axis. The measure of the tendency of the system to rotate about the origin is called the moment about the origin and is defined as the sum of the n products, m sub I, x sub I. What we're saying is that the x-axis represents the seesaw and the origin represents the fulcrum. we put masses both to the left and to the right of our origin. We defined the moment about the origin m sub 0, which is m sub 1 x sub 1 plus m sub 2 x sub 2 plus m sub 3 x sub 3 plus dot 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 plus m sub n minus 1 x sub n minus 1 plus m sub n x sub n. In this equation, the x sub I values are positive to the right of the origin and negative to the left of the origin. If the moment about the origin, m sub 0 equals 0, then the system is said to be in equilibrium, which means that the seesaw balances. So looking at our problem above with the two animals, m sub 0 is equal to 6 times negative 5 plus 5 times 6 is equal to 0, and that means that the system balances. If a system is not in equilibrium, we can move the fulcrum so that it will be. So for a system not in equilibrium, the center of mass is defined as the point x bar at which the fulcrum could be relocated to attain equilibrium. If the system is translated x bar units, each coordinate x sub I now becomes x sub I minus x bar, and therefore the moment of the translated system becomes 0. So the moment of our translated system, now in equilibrium, is given by summation I equals 1 to n of m sub I times the quantity x sub I minus x bar. And that is equal to summation I equals 1 to n of m sub I x sub I minus summation I equals 1 to n of m sub I x bar. And that is also equal to summation I equals 1 to n of m sub I x sub I minus x bar summation I equals 1 to n of m sub I. And since this is an equilibrium, it's set equal to 0. So we can solve for x bar. And we get x bar is equal to summation I equals 1 to n of m sub I x sub I over summation I equals 1 to n of m sub I. This is simply equal to m sub 0 over m, where m sub 0 is the moment about the origin, and m is simply the total mass of the system. So examine the system in number 2. We have a mass of 10 at negative 8, a mass of 6 at negative 5, a mass of 12 at negative 2, a mass of 4 at 1, and a mass of 8 at 5. It is clearly not in equilibrium relative to the origin. There's much more mass on the left of the origin than to the right. We'd like to find the center of the mass of this system, which is the point where we can relocate the center where the system would balance. So using our formula, x bar is equal to m sub 0, the moment about the origin, which is 10 times negative 8 plus 6 times negative 5 plus 12 times negative 2 plus 4 times 1 plus 8 times 5 over the total mass of the system, which is 10 plus 6 plus 12 plus 4 plus 8. This gives negative 90 over 40, and our x bar is equal to negative 2.25. If we move the fulcrum to that point, negative 2.25, the system will balance. Rather than talking about the center of mass, we can define the center of gravity, which is the average location of the weight of the object. Since F is equal to ma, we can use our formula replacing m with ma. The a's cancel, and the center of gravity and the center of mass have the same location. Since most of the time we are working on Earth, we will refer to it as the center of gravity. We can extend the concept of moment to 2 dimensions by considering a system of masses located in the xy plane. So suppose we have point masses m1, m sub 2, m sub 3, m sub n, be located at the points x1, y1, x2, y2, xn, yn. We define the moment about the y-axis as my, which will be m1 x1 plus m2 x2 plus m3 x3 plus plus m sub n minus 1 x sub n minus 1 plus m sub n x sub n. We define the moment about the x-axis as mx, which is m1 y1 plus m2 y2 plus m3 y3 plus plus m sub n minus 1 y sub n minus 1 plus m sub n y sub n. So we now can find our center of mass, x bar, y bar, and we could also refer to that as the center of gravity, with x bar equaling my over m, and y bar equaling mx over m, where m is equal to m1 plus m2 plus m3 plus plus mn, which is the total mass of the system. Let's see how that is used. In number 3, we're asked to find the center of mass or the center of gravity of the 4 point masses. We have m sub 1 is 8 at the point 4, negative 2. M sub 2 is 3 at the point negative 1, 0. M sub 3 is 10 at the point negative 3, negative 4. And M sub 4 is 4 at the point 5, 3. I suggest that you use the graph and draw circles of relative size and try to determine where you believe the center of gravity or center of mass is. Determining where you believe the center of mass is a good way for you to understand how the formula works. Break it up into 2 pieces. Think of the x-axis. Do you think that the center of mass is below or above the x-axis? Think of the y-axis. Do you think the center of mass is above or below the y-axis? What is the point at negative 1, 0, mass of 3 affecting? Is it affecting the x or y moment? We start out by finding little m, which is the mass of the entire system, which is 8 plus 3 plus 10 plus 4, which is 25. M sub y is the summation of our m's times our x variables. So it's 8 times 4 plus 3 times negative 1 plus 10 times negative 3 plus 4 times 5, which is 19. And m sub x is equal to our masses times our y variables. So that is 8 times negative 2 plus 3 times 0 plus 10 times negative 4 plus 4 times 3, which is negative 44. X bar is equal to my over m, which is 19 over 25, and y bar is equal to mx over m, which is negative 44 over 25. So x bar, y bar is the point 0.76, negative 1.76. We show the center of gravity or center of mass in green. It should be clear that it should be below the x-axis, as most of the mass is concentrated there. Having it slightly to the right of the y-axis also makes sense. Although there is more mass to the left of the y-axis, the mass to the right of the y-axis is further away from it, affecting its moment. Students can get confused in using these formulas. The moment about the y-axis, m sub y, uses x's, while the moment about the x-axis, m sub x, uses the y variables. But in calculating the center of gravity, the point x bar, y bar, x bar uses m sub y and y bar uses m sub x. It is confusing. So it's actually easier to calculate x bar and y bar immediately after you calculate m, as x bar ultimately uses the x variables and y bar ultimately uses the y variables. We can see the results, and you can see it's the same calculation, but no worries about calculating m sub x and m sub y. In number 4, you are given a geometric shape and you would like to find its center of mass. To find the center of mass of a geometric shape made up of rectangles, triangles, trapezoids, circles, and other regular figures, it is best to create a coordinate system similar to what we did in work and fluid force problems and transfer our shape onto that grid. We can then find the coordinates of the centroid, or the center of each shape, and the mass of each shape, which will be its area. So we will then have a series of point masses similar to the problems we did before, and we can use our formulas to find the center of mass. We transferred our shape onto the grid and chopped it up into 4 rectangles. There are numerous ways to do this. There's not only just one, and it does not matter how you do it. The centroid of the first rectangle is the point 1, 2. And since it is 2 by 4, its mass is 8. The centroid of the second rectangle is the point 2.51, and since its dimensions are 1 by 2, its mass is 2. The centroid of the third rectangle is the point 4, 1.5, and since its dimensions are 2 by 3, its mass is 6. And finally, the centroid of the fourth rectangle is the point 6, 0.5, and since its dimensions are 2 by 1, its mass is 2. The moment about the y-axis, my, uses the x variables, and we get 8 times 1 plus 2 times 2.5 plus 6 times 4 plus 2 times 6, getting 49. The moment about the x-axis is m sub x, and that uses the y variables, and we get 8 times 2 plus 2 times 1 plus 6 times 1.5 plus 2 times 0.5, and that gives us 28. The total mass of the object is 8 plus 2 plus 6 plus 2, getting 18. So x bar is m sub y over m, and we get 49 over 18. Y bar is 28 over 18. So the point x bar, y bar is 2.722, 1.566. We see the point representing the center of mass pulsing on the figure. It is possible for the center of mass to be a point outside the figure. In the next slide, we will examine what that actually means physically. It is possible for the center of mass, or center of gravity, to lie outside the shape we are evaluating. Consider the L-shaped figure on the screen. We move our figure to a grid and show that we have 2 rectangles, a vertical one and a horizontal one. For the vertical one, the centroid is the point 0.52, and its mass, since the shape is 1 by 4, is 4. The other has center at 2.5, 0.5, and since this is 1 by 3, its mass is 3. So m sub y is 4 times 0.5 plus 3 times 2.5, which is 9.5. And m sub x is 4 times 2 plus 3 times 0.5, which is also 9.5. The mass of the shape is 4 plus 3, which is 7. So both x bar and y bar are 9.5 over 7, and the centroid is the point 1.357, 1.357, which is clearly outside the shape. As humans, we have a center of mass or gravity that is approximately located, depending on factors such as gender, height, and weight, 4 inches below the navel. The human body loses its balance when its center of mass falls outside its base of support. This can happen for brief times as we move through the air, as shown. We now take our shape and move it into 3 dimensions. We take a thin, flat plate of material with uniform density, meaning it is constant throughout the same material. We call this plate a planar lamina. For planar laminas, density will be a measure of mass per unit area and is designated by the Greek letter rho. The center of mass, also called the centroid of a planar lamina, is the point x bar y bar and is the balancing point. For circles and rectangles, the center of mass is their center. If the planar lamina is not a circle or a rectangle, finding the center of mass is not as easy. Using Riemann sums, we can generate moments about the x and y axes and then find the center of mass of a lamina of uniform density. Let f and g be continuous functions such that f of x is greater than or equal to g of x on the interval a to b. Consider the lamina of uniform density rho bounded by y equals f of x and y equals g of x on the interval a to b. The moments about the x-axis and y-axis are m sub x is equal to rho integral from a to b of f of x plus g of x all over 2 times the quantity f of x minus g of x dx. And this can be simplified into 1/2 rho integral from a to b of the expression f of x squared minus g of x squared dx. M sub y is rho integral from a to b of x times the expression f of x minus g of x dx. And our m, little m, is rho integral from a to b of f of x minus g of x d of x, which is simply the mass of the lamina. So as before, the center of mass, x bar y bar, which is the centroid, is given by x bar is equal to m sub y over m, and y bar is equal to m sub x over m. We will see this in the next few examples. In number 5, you are asked to find the centroid of the region of the planar lamina with density rho equals 1, with a surface whose graphs are bounded by the function f of x equals x squared and y equals 4. It should be obvious that the center of mass lies on the y-axis. So place a mark on the y-axis where you believe the centroid to be and give a value to it. There are 3 steps to a problem like this. First, we have to find little m, which is the total mass of our object. Secondly, we need to find m sub y and m sub x, which is the moment about the y-axis and a moment about the x-axis. And from that, we can find and locate our centroid by finding the point x bar, y bar. In many of these problems, a calculator is either necessary or advisable to use in order to perform the integration. Here's one that we can do without the use of a calculator. To find little m, we set up the integral from -2 to 2 of 4 minus x squared dx, which is equal to 2, the integral from 0 to 2 of 4 minus x squared dx. Integrating, we get 2 quantity 4x minus x cubed over 3, evaluated from 0 to 2, and that gives 2 quantity 8 minus 8 thirds, or 32 thirds. M sub y equals the integral from -2 to 2 of x quantity 4 minus x squared dx. And this gives 2x squared minus x to the fourth over 4 evaluated from -2 to 2. And this, when calculated, is the quantity 8 minus 4 minus the quantity 8 minus 4, which is 0. M sub x equals 1/2 the integral of 4 minus x squared times 4 plus x squared, which is 16 minus x to the fourth, evaluated from -2 to 2. Realizing that this is even, we can double it and integrate from 0 to 2, and we get 16x minus x to the fifth over 5, evaluated from 0 to 2, and we get 128 over 5. As we knew all along, our x bar would be 0. Our y bar is 128 over 5 divided by 32 over 3, which is 128 over 5 times 3 over 32, which is 12.5 or 2.4. So our centroid is at the point 0, 2.4. In number 6, you are asked to find the centroid of the planar lamina whose region is bounded by y equals 4 minus x squared, y equals x plus 2, with rho is equal to 1. Again, it is suggested that you put a dot on the diagram to show where you believe the centroid to be. In setting up the integrals, we will use the calculator to determine the definite integrals rather than doing it algebraically, even though these problems are simple enough to do algebraically. M sub y equals the integral from -2 to 1 of x times 4 minus x squared minus the quantity x plus 2, which is 2 minus x squared minus x dx. And that gives -9/4. M sub x is equal to 1/2 the integral from -2 to 1 of 4 minus x squared squared minus x plus 2 quantity squared dx, and that is 54/5. And finally, little m is equal to the integral from -2 to 1 of 4 minus x squared minus the quantity x plus 2 dx, and that gives 9/2. So x bar is equal to -9/4 divided by 9/2, which is the same as multiplying by 2/9, and we get -1/2. Y bar is equal to 54/5 divided by 9/2, which is multiplying by 2/9, and that is 12/5. So our x bar, y bar centroid is the point -1/2, 12/5. In number 7, we are asked to find the centroid of the planar lamina whose region is bounded by y equals sine of x, y equals cosine of x, x is equal to 0, and whose rho is equal to 1. We graph the function and find that sine of x and cosine of x intersect at x is equal to pi over 4. So m sub y equals the integral from 0 to pi over 4 of x quantity cosine of x minus sine of x dx, which is 0.111, while m sub x is equal to 1/2 the integral from 0 to pi over 4 of cosine squared of x minus sine squared of x dx, which is equal to 0.25. Small m is equal to the integral from 0 to pi over 4 of cosine of x minus sine of x dx, which is equal to 0.414. So x bar is equal to 0.111 divided by 0.414, which is 0.268, while y bar is equal to 0.25 over 0.414, which is 0.604. So our centroid is the point 0.268, 0.604 as shown on the graph. In number 8, we are given a right triangle that is formed with the legs being the x and y axes, and the hypotenuse, the line y equals 4 minus x. We would like to show that the centroid of the triangle is the intersection of its median lines. In a triangle, the median is a line that goes from any vertex to the opposite side. So the median from the point 0,4 to the point 2,0 is the line y equals negative 2x plus 4. The median from the point 4,0 to the point 0,2 is the line y equals negative x over 2 plus 2. And the median from the point 0,0 to the point 2,2 is the line y is equal to x. They clearly intersect at one point. We would like to say and show that that point is the centroid of the triangle. In this case, there is only one function, f of x, which is 4 minus x. So m sub y equals the integral from 0 to 4 of x times 4 minus x dx, which is 32/3. M sub x is 1/2 the integral from 0 to 4 of 4 minus x quantity squared dx, which is 32/3. M is equal to the integral from 0 to 4 of 4 minus x dx, which is 8. So x bar is 32/3 over 8, which is 4/3, as is y bar, 32/3 over 8, which is 4/3. So therefore, x bar, y bar is the point 4/3, 4/3. Finally, we show the point 4/3, 4/3 satisfies each of the median lines. The median from 0,4 to 2,0 gives y is equal to negative 2 times 4/3 plus 4, and that is 4/3. The median from 4,0 to 0,2 is y equals negative 1/2 times 4/3 plus 2, and that also is 4/3. And the median from 0,0 to 2,2 is the line y equals 4/3.